Problem-solving strategies for solving these energy conservation problems are to, number one, define the system. Typically, that's the object in question that is subject to the various forces. We're interested in the motion of that object, how fast it's going, how far it goes, etc. Beyond defining the particular object, we want to identify the specific forces that are acting in the system. And so we have simple questions to ask ourselves. Does the object move up and down? If so, we have to include gravitational potential energy. Are there springs present in the system? If that's the case, we need to include the potential for spring potential energy. If there are no springs, we don't have to consider spring potential energy, because if the springs aren't there, they definitely won't be storing energy. Is there friction in the system? If so, we'll have to include a term for thermal energy as well, for those energy losses. And something else to be aware of are there other sources or sinks of energy? If that's the case, we'll have to include those in the energy equation as well. By sources and sinks of energy, we specifically are considering external forces that might be acting on the object, in addition to these external forces that we've internalized to our system through the process of making them potential energies. You may also see, for example, for sources or sinks of energy, you might see, for example, chemical potential energy. In that case, you would have energy from gasoline driving the car. You might have energy from an explosion that pushes a cannonball out of the cannon. You have other possibilities for energy being added to the system or taken out of the system. For our first example of this, we have an Atwood machine. We have two blocks. Block A has a mass of 1 kilogram. Block B has a mass of 2 kilograms. When we release the blocks from rest, we know how to solve this from Newton's equations. We know how to look at the forces acting on each block, finding their acceleration, and thus finding their velocity at some later time. But we can also consider this problem from the perspective of energy, where we know that block 2 is heavier than block 1, so we know the system will tend to move in this manner. And so if we're seeing this motion, this velocity, we can also consider that velocity in terms of potential energy. If we know that this block is going down and this block is going up, we can consider that in terms of gravitational potential energy. So we can treat this sort of problem in terms of our energies, as well as looking at them from the perspective of Newton's laws. So in this case, we're being asked, if the blocks are released from rest, what is their total kinetic energy when block B has fallen by 25 centimeters? So we can look and we can say, all right, this block is going to move up, this block is going to move down, so we have to include kinetic energies. They're moving up and down, so we have to include gravitational potential energy. There are no springs here, so we do not have to include spring potential energy. And the system is frictionless, so we don't have to consider thermal energy. Furthermore, we know that the blocks are released from rest, so the initial kinetic energy would be 0 in that case. Depending on where we define our reference point, we could have different values of the gravitational potential energy. But again, that doesn't matter where we count the reference point. It's the change from the initial gravitational potential to the final that really matters. And so now that we have the energies, we can set up the equation, solve the actual values. For our next example, we have a block that's accelerated from rest by a compressed spring. The block is accelerated over a frictionless part of the floor, and once the block leaves the spring, the block travels onto a horizontal floor with kinetic friction, and the frictional force stops the block after it travels a distance. So what we can see here is that our block is moving back and forth, so there's definitely kinetic energy. The block is moving completely horizontally, so there's no gravitational potential energy to consider. There's a spring involved, so we need spring potential energy, and there's friction involved, so we'll need to include thermal energy. What we can say, though, depending on where we want to pick the amounts, what we can say from this equation is that initially there's no kinetic energy. Initially, all of the energy is in the spring. When the spring is fully decompressed, when the spring is released, the spring potential energy goes to zero, and all of that energy becomes kinetic energy. Once the block starts sliding across the rough surface, this kinetic energy is leached away as thermal energy due to friction. And at the end, when the block stops, its kinetic energy is zero, and all of the energy is thermal energy. So what we're seeing in this sort of situation is we have spring potential energy, which is converted to kinetic energy, which is converted to thermal energy. Why this is important is that when we're conserving energy, we're looking at energy initial equals energy final. And so we can look at the change in energy from case 1 to case 2, from case 1 to case 3, from case 2 to case 3. It doesn't matter, and in fact we could set up a larger equation where we actually equate all three energies, and we could find out how much the spring is compressed, how fast the block is going when it leaves the spring, how far it goes before friction stops it. In our last example, we have a block that is released from rest down an inclined plane with friction. The block hits the spring and compresses the spring. Here we're told how much force will compress the spring by a certain amount. That is giving us the spring constant K. The block compresses the spring, and we want to know how far the block moves down the inclined plane before the spring stops it. So when we look at the situation, we see that we have motion, so we're going to have to include kinetic energy. If the block is moving downwards, there is a vertical component to that, and so we have to include gravitational potential energy. As the block moves, it's going to hit a spring, so we have to include spring potential energy. And if there's friction in the plane, we have to include thermal energy. So in this case, we'll have to include all parts. However, we can say initially we're not moving, so initially there's no kinetic energy. Initially, the block isn't even touching the spring, so initially there'd be no spring potential energy. What we're seeing here is that there's gravitational potential energy. When we release the block, the gravity makes the block slide down. That's a loss of gravitational potential energy as that energy is turned into speed, turned into motion of the block, plus thermal energy as we overcome friction. And then at the end, we end up hitting the spring, compressing it, so we end up with some spring potential energy.